Dimensionless Numbers in Fluid Mechanics. A listening chapter for chemical engineers. The purpose of dimensionless thinking. Engineering is, at its heart, a science of competition. In almost every process you can name, something is trying to happen, and something else is resisting it. Inertia wants to carry a fluid forward. Viscosity wants to slow it down. Pressure wants to drive a gas through a nozzle. The speed of sound sets an upper limit on how fast information about that pressure can travel. A surface wants to stay round. Flowing liquid wants to deform it. Heat wants to spread by diffusion. Flowing fluid wants to carry it downstream instead. These competitions are real, and they determine how systems behave. Dimensionless numbers are the language we use to express those competitions in a form that is universal, independent of whether the measurement was made in meters or feet, in pascals or atmospheres, in grams or pounds. The key insight behind dimensional analysis is that units are a human invention. Physics is not. A genuine physical relationship should not depend on the arbitrary choice of measurement system. Dimensional homogeneity, the requirement that every term in a physical equation carry the same units, is not a bookkeeping rule. It is a statement that the universe is internally consistent. You cannot add pressure to velocity unless one of them has been converted into the same kind of quantity as the other. From this requirement, combined with the formal machinery of the Buckingham pi theorem, a system that appears to depend on many separate variables, pipe diameter, velocity, density, viscosity, gravity, surface tension, temperature, can be collapsed into a smaller number of dimensionless ratios that carry all the physical content. For chemical engineers in particular, this matters enormously. Industrial flow systems almost never involve one effect in isolation. A heat exchanger may involve turbulence, viscous losses, and convective heat transfer simultaneously. A stirred reactor may involve vortex formation, gas dispersion, droplet breakup, heat removal, and reaction time all at once. A spray dryer combines gas flow, droplet trajectories, evaporation, and particle drying in a single moving space. Dimensionless numbers allow the engineer to ask, before a single equation is written, which of these effects is actually winning? That question, asked early, is often the most valuable act of engineering judgment. Reynolds number, inertia against viscosity. Picture it. A slender thread of dye injected into water moving slowly through a glass tube. At low flow speeds, the thread holds its shape, drifting in an unbroken line down the center of the pipe. Increase the speed beyond a certain threshold, and the thread suddenly breaks apart, writhing, diffusing, scattering into turbulent disorder. Nothing changed except the speed. The fluid was the same. The tube was the same. The dye was the same. What changed was the balance between inertia and viscosity, and that balance is what Reynolds number measures. When it is low, viscosity has enough authority to suppress disturbances. Every small perturbation that forms in the flow is damped before it can grow. Fluid layers slide smoothly past one another. Laminar motion. When it is high, inertia dominates, and the same perturbations can amplify. Eddies form, mix, and interact. For flow inside a circular pipe, engineering practice places the laminar regime below roughly 2,100, the transitional regime between about 2,100 and 4,000, and fully turbulent flow above about 4,000. These are guides, not laws. They shift with inlet conditions, surface roughness, non-Newtonian behavior, and pipe geometry. Use them to orient yourself, not to replace judgment. For a chemical engineer, Reynolds number is not merely about whether a dye streak stays straight in a glass tube. It decides which friction factor correlations apply in a pipeline. It determines whether a heat exchanger will have vigorous mixing, or whether it will operate in an orderly laminar regime, where the thermal boundary layer grows thick and heat transfer resistance builds. In a packed bed, it distinguishes the creeping flow regime, where Darcy's law applies, from the inertial regime, where pressure drop scales differently with velocity. In slurry lines, It helps diagnose whether there is enough turbulence to keep particles suspended. One of its most important lessons is about scale-up, and this lesson is often learned the hard way. A pilot plant channel may look geometrically identical to a full-scale industrial duct, but if the Reynolds numbers differ, the internal flow physics can be completely different. Two geometrically similar systems that share the same Reynolds number will behave the same hydrodynamically. Their velocity profiles, turbulence intensities, and pressure drop coefficients will correspond. Two that do not share it will not, even if they look alike. This is the practical meaning of dynamic similarity. Appearance is not physics. Mach number, flow speed against the speed of information. Every fluid is also a communication medium. Changes in pressure, created by a valve slamming shut, a pump speeding up, or a constriction in a line, travel through the fluid as pressure waves at a finite speed. In ordinary air at room temperature, that speed is roughly 343 meters per second. In liquid water, it is much higher, near 1,500 meters per second, which is why water hammer in a liquid system can be so violent. In a slow-moving gas, these pressure waves travel far faster than the bulk flow, so every part of the flow knows what every other part is doing. Density barely changes in response, and the fluid behaves as if it were incompressible. Bernoulli-style thinking works well. Now raise the gas velocity. As the flow approaches the speed of sound, something fundamental changes. The flow and the pressure information are moving on comparable timescales. Density can no longer be treated as constant. Temperature, pressure, and velocity become tightly coupled. The ratio of flow speed to local speed of sound is Mach number, and crossing from low values to high values is not a smooth transition. It is a regime change. Mach number is not exclusively an aerospace concept. It appears whenever high-speed gas flows through process equipment. A relief valve, venting gas from a pressurized vessel. A steam ejector drawing vacuum. A choked orifice in a flow measurement device. A high-pressure gas feed to a reactor. When the gas velocity reaches a significant fraction of the speed of sound, roughly above about 0.3, compressibility can no longer be ignored. In such conditions, reducing downstream pressure further cannot increase the mass flow rate because sonic conditions have already been reached at the throat and the flow is choked. Extending Bernoulli intuition into this regime produces errors. Mach number is the first number that tells you whether you are in that territory. Capillary number, viscosity against interfacial tension. Interfaces are stubborn. Pour oil into water, stir vigorously, and the mixture emulsifies, but stop stirring, and the droplets gradually coalesce, and the oil layer reforms. Given time, the interface reasserts itself. It resists deformation with a force per unit length, called interfacial tension, and it wants to minimize its area. Now introduce flow. Moving liquid exerts viscous stresses on any interface it encounters. Whether that interface holds its shape or yields, whether it stays round, elongates, or breaks into smaller droplets, depends on the competition between viscous stress and interfacial resistance. That competition is capillary number. At small values, surface tension wins. An interface resists the flow. Droplets stay round. Fluid remains pinned in pores. Thin films hold together. At large values, viscous stress wins. Droplets deform and break. Interfaces are dragged and stretched. Fluids that were trapped are mobilized. Chemical engineers encounter this competition everywhere. In enhanced oil recovery, whether oil trapped in the pore spaces of a reservoir rock can be displaced by flooding depends critically on whether viscous driving forces are large enough relative to capillary holding forces. In emulsion manufacture, adjusting flow rate, surfactant loading, or the viscosity of the continuous phase all shift capillary number and change the droplet size distribution. In liquid-liquid extraction, it influences how finely one phase disperses in the other. In microfluidic droplet generators, it is the primary design parameter. A T-junction or flow-focusing geometry is tuned specifically to produce droplets of a target size by controlling the ratio of viscous to interfacial forces. Do not confuse capillary number with Weber number, even though both involve surface tension. Weber number compares inertia with surface tension. It governs high-speed droplet breakup, jet atomization, and sprays. Capillary number compares viscous stress with surface tension. It governs slow viscous deformation, film coating, microfluidic plug formation, and porous media displacement. Both live in the same interfacial world, but they rule different speed regimes within it. Gravity, pressure, surface tension, and unsteadiness. Not all flows have the luxury of a closed boundary. Rivers, drainage channels, spillways, and sloshing liquid in tankers all carry a free surface exposed to the atmosphere, and that surface can support waves. Whether gravity waves can travel upstream or are swept downstream by the current, that is the question Froude number answers. When it is below 1, the flow moves slowly relative to its own wave speed, and information can propagate upstream. Downstream conditions influence what happens upstream. When it exceeds 1, the flow outruns its wave speed, and information travels only downstream. This distinction controls how hydraulic controls such as weirs, gates, and sluices operate, why hydraulic jumps form where they do, and why energy dissipation downstream of a spillway is so dramatic. Pressure itself is the natural driving variable in pipe flow, and how large the driving pressure difference is compared to the flow's kinetic energy is expressed by Euler number. For most practical resistance correlations, it appears implicitly through pressure drop coefficients. Its more specialized relative, cavitation number, focuses attention on the pressure margin above vapor pressure. When pressure drops below this threshold, downstream of a rapid constriction, at the inlet of a pump near a partially closed valve, a liquid can locally boil at room temperature, forming vapor bubbles that collapse violently in higher pressure regions. Pump specifications include a required net positive suction head precisely because cavitation at the inlet is destructive. Cavitation number is the dimensionless measure of how safe a given operating condition is from this threshold. Move to smaller scales or higher speeds, and surface tension reasserts itself in a different competition. When a liquid jet exits a nozzle, or when a spray atomizes into droplets, the contest is no longer between viscosity and surface tension, but between inertia and surface tension. Weber number captures this. Low values mean the interface resists breakup. A jet tends to stay intact or break into large drops by Rayleigh plateau instability. High values mean inertia dominates. Atomization is vigorous and droplets are fine. Inkjet printers, agricultural sprayers, fuel injectors, and spray dryers all sit in regimes where Weber number is the governing parameter for droplet size. For bubbles and large droplets in relatively quiescent fluids, gravity adds its own distorting role. A tiny bubble stays nearly spherical because surface tension dominates the pressure difference across its surface. A large bubble flattens, elongates, or caps because buoyancy-driven pressure differences grow large enough to overcome interfacial resistance. Bond number, comparing gravitational body forces to surface tension, captures this transition. Small values mean round interfaces. Large values mean gravity-distorted ones. This matters in bubble columns, flotation systems, and any reactor where gas-liquid contact area is important. Not every important competition is steady. A cylinder held in a crossflow sheds vortices alternately from each side, imposing periodic forces at a frequency that depends on diameter and velocity. Strouhal number is the dimensionless shedding frequency. When it matches a structural natural frequency, resonant vibration results. Heat exchanger tube bundles, thermowell probes, chimney stacks, bridge cables, and submarine structures are all at risk if Strouhal number is not checked in design. The quiet hum of wires in a wind, the vibration of a flagpole, these are everyday instances of the same phenomenon. Heat and mass transfer numbers. Follow a fluid element as it moves through a heat exchanger. Heat tries to diffuse from the hot wall into the fluid by molecular conduction. At the same time, the bulk motion of the fluid tries to carry that heat downstream before it has time to penetrate. Whether the energy exchange is dominated by molecular diffusion or swept away by flow is expressed by Piclet number, the ratio of advective transport to diffusive transport. At low Piclet number, diffusion is fast relative to flow, and thermal boundary conditions spread their influence broadly in both directions. At high Piclet number, convection dominates, and the heat stays concentrated near where it entered. An identical argument applies to mass transfer, substituting species diffusivity for thermal diffusivity. Prandtl number answers a closely related but architecturally different question. In flow over a heated wall, two layers grow away from the surface, a velocity boundary layer, where the fluid accelerates from rest at the wall to the free stream speed, and a thermal boundary layer, where temperature adjusts from the wall temperature to the free stream temperature. These two layers need not be the same thickness. Prandtl number is the ratio of momentum diffusivity to thermal diffusivity, and it sets the ratio of these thicknesses. For air, near 0.7, the thermal layer is slightly thicker than the velocity layer. For heavy oils, it can be hundreds or thousands, meaning heat barely penetrates while momentum spreads broadly. A dramatic mismatch with profound consequences for heat exchanger sizing. For liquid metals, it falls below 0.1, and heat diffuses far faster than momentum. These differences shape the Nusselt number correlations that engineers use every day. Schmidt number plays for mass transfer exactly the role Prandtl number plays for heat. It compares momentum diffusivity with species diffusivity. In gases, it is typically near unity. Momentum and mass diffuse at comparable rates. In liquids, it can reach 1,000 or more, because molecular diffusion of solutes is far slower than viscous momentum transfer. Large Schmidt numbers mean a very thin concentration boundary layer, riding inside a much thicker velocity boundary layer, steep concentration gradients near walls, and high sensitivity to wall conditions. Nusselt number converts convective heat transfer from a physical rate into a dimensionless performance metric. Think of it as the answer to this question. How much better is convective heat transfer than pure conduction through a stagnant fluid layer of the same thickness? A value of 1 means no improvement. The fluid might as well be stationary. A value of 100 means convection is 100 times more effective at moving heat across the fluid than conduction alone. Nusselt number correlations, expressed as functions of Reynolds and Prandtl for forced convection, or of Grashof and Prandtl for natural convection, are among the most used formulas in engineering. Sherwood number does for mass transfer exactly what Nusselt number does for heat. It compares the actual mass transfer rate across a boundary layer to the rate that diffusion alone, through a stagnant film, would produce. Correlations for Sherwood number almost always mirror those for Nusselt. Replace Prandtl with Schmidt. Replace Nusselt with Sherwood, and the mathematical form is the same. This is one of the most powerful bridges in all of chemical engineering. An entire library of heat transfer knowledge becomes directly available for mass transfer design by a single substitution. Inside a catalyst pellet or drying particle, however, the fluid side story is only half the picture. Biot number asks whether internal resistance within the solid is comparable to, or much larger than, external convective resistance at the surface. When it is small, the solid interior stays nearly uniform in temperature or concentration. The lumped system assumption holds. When it is large, internal gradients matter, and the full distributed transport problem must be solved. For catalyst effectiveness, particle drying, and heat treatment of materials, Biot number determines which analysis is actually necessary. Two further numbers complete this family. Fourier number is dimensionless time for diffusion. It measures how far a diffusive signal has penetrated a given length scale during a given period. Early time behavior, before diffusion has reached far, lives at small Fourier numbers. Long time behavior, when the system has nearly equilibrated, lives at large ones. Lewis number. The ratio of thermal diffusivity to mass diffusivity enters whenever heat and mass transfer occur simultaneously. Drying, evaporating sprays, humidification, combustion, gas absorption. When Lewis number departs significantly from 1, the thermal and concentration profiles evolve on different timescales and must be tracked separately. Buoyancy deserves its own place in this family. When temperature or concentration differences create density gradients, they can drive fluid motion even without any externally applied pressure gradient. Grashof number characterizes this, comparing buoyancy forces to viscous forces. Rayleigh number, its product with Prandtl, is the more commonly used criterion for the onset and intensity of natural convection heat transfer. In large storage tanks, open reactor vessels, and passive cooling systems, Grashof and Rayleigh numbers decide whether natural convection contributes meaningfully to heat removal or can be safely neglected. particles, beds, reactors, and rheological fluids. Add a second phase, solid particles, liquid droplets, or gas bubbles dispersed in a carrier fluid, and the problem deepens immediately. Each dispersed element has its own inertia, and whether it responds quickly to the surrounding flow or carries its momentum into regions where the flow has already moved on determines its trajectory, its probability of wall impact, and its residence time in the system. Stokes' number captures this. It is the ratio of a particle's inertial relaxation time to the characteristic time of the surrounding flow. Small values mean particles follow streamlines faithfully. Large values mean particles carry momentum across streamlines, impact surfaces, or separate from the carrier. Cyclone separators, spray dryers, aerosol filters, and pneumatic conveying lines all depend on engineering Stokes' number to steer particles where they are wanted, or away from where they are not. When buoyancy is the mechanism rather than inertial lag, Archimedes' number takes over. It compares gravitational forces driven by density differences with viscous forces, and it appears naturally in settling, rising bubbles, and the onset of fluidization. A fluidized bed is, in essence, a system where conditions have been tuned so that fluid drag on the particles exactly balances their effective weight. Archimedes' number is the dimensionless statement of when that balance is achievable and what flow regime the bed is in. In chemical reactors, chemistry and transport race each other. Whether a reactor operates at its intrinsic kinetic rate, or whether conversion is limited by mixing, diffusion, or residence time, that is answered by Damköhler number. It compares the rate of reaction with the rate of a relevant transport process. Small values say material will be swept through and out before the reaction proceeds significantly. Kinetics is underutilized, and the reactor is wasteful of its own potential. Large values say the reaction is fast relative to transport. The system is limited not by intrinsic chemistry, but by how quickly reactants are brought together, or how quickly products are removed. Tubular reactors, packed beds, bubble columns, stirred tanks, bioreactors, and membrane reactors all require a Damköhler number assessment before meaningful design can begin. Then there are fluids that remember. Most of what fluid mechanics teaches assumes that the relationship between stress and deformation rate is instantaneous. Apply a stress, get a response immediately, remove it, and the fluid forgets. Many real fluids, polymer melts, concentrated polymer solutions, biological gels, food pastes, drilling muds, paints, carry a memory of past deformation. Weissenberg number measures whether elastic effects are significant by comparing the fluid's relaxation time with the characteristic rate of deformation in the process. When it is large, elastic effects dominate. A polymer solution can climb a rotating rod instead of being flung outward. An extrudate swells upon exiting a die, and the fluid develops normal stress differences with no analog in Newtonian behavior. Deborah number is closely related, but subtly different. It compares the fluid's relaxation time with the observation timescale of the process. A material might appear solid over a short test. Its relaxation time is longer than the observation. The same material might flow perceptibly over a long one. Glaciers are the classic illustration. On human timescales, ice seems rigid. On geological timescales, it flows. For polymer processing, the distinction between these two numbers, when each one governs, is part of the working vocabulary of the practitioner, and it serves as a reminder that solid and fluid are not fixed categories, but descriptions of a ratio between material time and process time. How the numbers compare. A useful way to hear dimensionless numbers is as a set of ongoing physical conversations. Reynolds asks whether the flow organizes itself into ordered layers or dissolves into turbulent disorder. Mach asks whether pressure information can keep up with the flow or is left behind. Froude asks whether gravity waves can communicate upstream or are swept away. Capillary and Weber ask about the fate of interfaces. Will surface tension hold them intact, or will viscous or inertial forces prevail? Euler and cavitation number ask whether the pressure field has room to maneuver above the vapor pressure floor. Strouhal asks whether periodic shedding is generating forces fast enough to threaten structural resonance. What enriches this conversation is that the numbers are not strangers to one another. They are related members of a family. Peclet number is Reynolds number multiplied by Prandtl number for heat, or by Schmidt number for mass. This single relationship immediately connects flow regime to the depth of a thermal or concentration boundary layer. Sherwood number is Nusselt number's mass transfer twin, making every heat transfer correlation available in a different form. Rayleigh number is the product of Grashof and Prandtl numbers, linking buoyancy to both the density stratification and the fluid's thermal diffusivity. Ohnesorg number sits at the intersection of viscosity, inertia, and surface tension, and understanding it requires simultaneously thinking in Weber, Reynolds, and Capillary terms. Some of the most challenging industrial situations are those where several numbers are simultaneously important, and none can be safely neglected. A bubble column may involve Reynolds, Froude, Bond, Sherwood, and Köhler all at once. A microfluidic droplet reactor operates at very low Reynolds number. The inertial world is nearly absent, but at capillary numbers that control plug formation, Peclet numbers that govern axial transport, and Köhler numbers that determine whether reaction completes before the plug exits the device. Identifying which numbers dominate and which are secondary is the first act of engineering judgment, and it cannot be replaced by computation alone. The engineer's synthesis. Experienced practitioners use dimensionless numbers in two distinct modes, and both matter equally. The first mode is diagnostic. Before committing to a model, a correlation, or a design, scan the numbers to understand what regime you are in. Is this pipe flow laminar or turbulent? Is this gas line compressible? Is this interface going to break up under process conditions? Is this reactor limited by kinetics or by mixing? Answering these questions with order of magnitude estimates takes minutes and prevents hours of misguided calculation. The second mode is scaling, using the numbers to translate knowledge from one system to another. A laboratory heat exchanger test generates Nusselt number data as a function of Reynolds and Prandtl numbers. Those same correlations describe the industrial scale exchanger, provided the geometry is similar and the controlling dimensionless groups fall in the same range. A small-scale stirred tank gives mass transfer data at specific Reynolds and power numbers. Those results can predict performance at larger scale if the same numbers are matched. A pilot fluidized bed establishes Sherwood number correlations. The full-scale bed follows the same correlation if Archimedes and Reynolds numbers are preserved. Dimensional analysis is, at its core, the key to trusted scale-up. The same numbers serve as diagnostic clues when things go wrong. A heat exchanger underperforming its rating? Check whether the flow is fully turbulent at the expected Reynolds number, whether fouling has effectively increased the Biot number, whether viscosity has shifted and moved the Prandtl number. A pump cavitating unexpectedly? Check whether the available net positive suction head still provides adequate margin above the cavitation number threshold. A reactor losing conversion with scale-up? Check whether Köhler and Peclet numbers have been preserved. If the scale-up changed resonance time distribution or reduced mixing intensity, the effective Köhler number may have dropped even though the reaction kinetics were unchanged. What connects all these numbers, and what gives them their lasting value, is that they are statements about physics written in a language that outlasts any particular piece of equipment, any particular fluid, and any particular set of units. They are the grammar in which fluid mechanics and transport phenomena speak to one another. Every number is, in the end, a question. Which effect wins here? Answering that question well, quickly with good judgment, before equations are written, is one of the deepest practical skills in chemical engineering. We have now moved through the full working vocabulary of dimensionless numbers, from Reynolds and Mach through Capillary and Weber, from Nusselt and Sherwood to Köhler and Deborah, organized around the question of which physical effects are competing inside a given flow. That is the engineering use of these numbers, and it is the right place to start. But there is a second way to encounter them, which is to ask not what they mean physically, but where they came from. Behind every dimensionless number is a person who is trying to solve a specific problem, in a specific place, at a specific moment in the history of the discipline. Osborne Reynolds was not trying to create a universal similarity parameter. He was watching dye break apart in a glass pipe in Manchester in 1883. Ernst Mach was not trying to define a speed ratio. He was photographing shock waves around supersonic bullets in Prague. Moritz Weber, whose name most students associate only with the ratio of inertia to surface tension, was the man who coined the very words Reynolds number and Froude number, giving the entire vocabulary of this subject its modern form. The chapter that follows tells those stories. It is meant to be listened to alongside the technical chapter, not instead of it, because the history does not replace the physics. It makes the physics easier to remember and considerably more interesting to think about.